many households, especially in the winter, the humidifier is a compact machine that makes use of simple principles to humidify indoor air. These processes can be explored in more detail using a fluid mechanical lens. The airflow into the system is driven by a pressure differential created by the pump. As these streamlines show, this airflow starts at the vent into the humidifier and then flows over all the electronics, providing some cooling effects. Then finally flows towards the eye of the pump through a small hole in the electronics casing. The governing equation for the airflow into the air half of the pump is the Bernoulli equation. Using Bernoulli's equation requires us to assume that the airflow is incompressible. The incompressible assumption breaks down when the flow is at a high velocity or the flow is enclosed. The velocity limitation is usually around 0.3 m, which our system does not approach. The flow is also completely open atmospheric pressure, so the enclosure breakdown does not occur. We also have to simplify our model to exclude viscous effects to use a Bernoulli equation. This simplification breaks down when viscous effects have a significant impact on the velocity of the flow. This breakdown tends to occur when the Reynolds number is low or when the fluid is close to a wall. In general, the fluid entering the system is not near any of the walls, so this does not cause a breakdown, although the Reynolds number for the system is low because of the low velocity of the flow. But due to air's low viscosity, Bernoulli's equation is still roughly accurate. Utilizing the Navier-Stokes equation will give you more accurate results with significantly increased complexity.
The mean flow approximation is an important assumption that lets us use an area average speed instead of accounting for the spatial variation of flow. This lets us write the equations governing the centrifugal fan more simply in terms of the flow rate, simplifying equations like the specific speed for the centrifugal fan. The geometry of the impeller, as well as the direction of rotation, indicate that the machine makes use of the centrifugal fan. Namely, the vanes extend radially outwards from the center, ejecting fluid tangentially. Following a streamline, you can see that the fan's rapid rotation creates a region of lower pressure that draws air through the eye of the fan. The air is accelerated due to the motion of the impellers and injected at high velocity tangentially.
At the bottom of the water reservoir, there's a spring-loaded valve that is pushed open when the water reservoir is put in place. There's a plastic piece with a slot for air to come in. The water flow into the bottom of the basin is governed by the Bernoulli equation. At the top of the reservoir, the pressure is atmospheric, the velocity is 0, and z is equal to h. And at the bottom, the pressure is still atmospheric, the water has velocity, and z is equal to 0. Solving this equation, you get that the velocity of the water is purely dependent on square root of 2gh. This value is not entirely accurate, as a valve is not only an outtake for the water, but also an intake for the air into the reservoir, so we add a fudge factor. However, this works for our purposes to show that the flow of the water is purely caused by the gravitational pressure force. This is the case until the basin fills up with enough water for the airflow slot on the reservoir to be covered up. Once no more air flows into the reservoir, the pressure drops in the reservoir as the water keeps flowing, which decreases the velocity of the water. The flow of the water continues to slow down until it reaches 0 when the difference in pressure is equal to rho gh.
Attached to the underside of the air fan is a small rotating siphon that sucks water up from the basin into the main body of the humidifier. In our analysis, we are treating the siphon as a skinny pipe, and it is governed by the modified Bernoulli equation to incorporate viscous losses. To use this form of the Bernoulli equation, we once again assume that the fluid is incompressible, and this assumption holds because the Mach number of the flow is much lower than 0.3. Unlike with the air, we can no longer assume that viscous forces are negligible due to the small diameter of the siphon and the increased viscosity of water when compared to the air. As the siphon rotates, angular momentum is imparted into the water by vanes that run along the siphon's length, pushing the fluid to the walls and raising its pressure. Like an ideal siphon, the Bernoulli equation tells us that water is drawn up the siphon due to a low pressure at the top exit relative to the bottom. As water flows up the siphon, the pressure of the fluid decreases due to its conversion into gravitational potential energy and viscous losses, which can be described by the modified Bernoulli equation.
The water drawn up the siphon is rotated at high speeds by the centrifugal fan and is subjected to a centrifugal force that drives the water towards the edges of the spinning disc. As the water is rejected towards the edges, it experiences shear forces due to the high speed rotation of the disc. Specifically, these shear forces create a velocity gradient in the water, which causes a deformation. This deformation, when the shear forces exceed the cohesive forces in the surface tension of the water, cause the water to physically disperse and create small droplets. This process is known as atomization.
In sum, the water is sucked up to the siphon and atomized due to the shear forces by the rapid rotation. The water and air are mixed together using a centrifugal fan, and the air carries the tiny water droplets along the streamlines, humidifying the outside air.